Hello everyone, welcome to the paper Linear Bandits with limited adaptivity and learning distributional optimal design. This paper is done by me, Yufei, and Jiaqi Yang and Yuan Zhou. First, for the title, you may want to ask what is linear bandits, what is limited adaptivity, and what is distributional optimal design. I will answer these questions in the presentation. Okay. So first, what is linear bandits? Linear contextual bandits, for short we call linear bandits, is a generalization of the so-called multi-armed bandits, where we can make decisions for personal needs. Since it is much more easier to have access to personalized data now. Like here in online ads, recommendation system, and the clinical trial, we have data for each customer and we want to give recommendations or treatments according to their personal context. Mathematically speaking, linear bandits is a bandit game that the player wants to learn the hidden vector theta. There are capital T time steps in total, and at each time t, the player will observe k contexts. Like these XTIs, which is the personal context of each customer, and they are from same distribution D. Sometimes we call this arms, and his job is to pick the best arms IT to maximize theta x. However, theta is hidden from him, and what he can know at each time step is only the reward, which is defined as theta x plus some sub-Gaussian noise epsilon. Notice that here, contexts represents individual features, actions represents recommendations, and the rewards represents outcomes. And his goal is basically to explore more about theta in the meantime minimize the measurement, which we call regret, which is defined as the expectation of the accumulated difference of our choice of x theta and the best choice of x theta. Also notice that the previous study has shown that the minimax optimal regret is here almost the order of square root of dt. And this will be our target goal in the later analysis. For the second question in the title, what is limited adaptivity? In this paper, we will first focus on a model with limited adaptivity called batch learning model. So what is batch learning? Instead of sequentially making decisions at each data point here, we group the data points into batches. And within a batch, the same policy is used to select actions for all data, and the rewards are observed only at the end of the batch. So the challenge here is first how to design the size of batches, and then how to design the decision policy within each batch to find the trade-off between optimal performance and fewer batches. That's why we call it limited adaptivity. Also notice here, we first assume that time steps are grouped into predefined batches. And in fact, we have also studied other batch grouping model, and I will mention them at the end. Our motivation here is first, of course, to save learning time and management costs by running the experiment in parallelization. And also batch learning has application in practice, like in this clinical trial example. Clinical trials runs in phases, which is equivalent to batches. So the key mathematical problem here is to find out a trade-off between the number of batches and the regret. And in particular, here we don't want to sacrifice much on regret, and still want to achieve the optimal performance, which means almost the same order of minimax optimal regret without batch constraint. And thus, the key problem in our paper is, what is the minimum number of batches needed to achieve optimal performance in online learning and decision making? In this paper, we proved the tight bound for this quantity, which is in fact pretty small, only at the order of log t. For previous results, such log t bound has been proved, like first, in a simpler setting which we call the multi-armed bandit setting. And then linear bandit setting is also considered in recent works by Han et al., but with some additional assumptions. Like first, they assume that context vectors are Gaussian, and then they assume that the number of actions k is pretty small. And it seems that their algorithm cannot be easily extended to general setting. In this work, we managed to do this by introducing new algorithms. So as I mentioned before, the main contribution of our paper is stated in Theorem 7 in the paper, which says that for linear bandits in batch learning model, it is possible to achieve a asymptotically minimax optimal regret, which is almost at the order of square root dt, using only log t batches. The key technical ingredients in our proof and algorithm design is first, we developed a batch elimination framework in our algorithm. And then by some technical analysis, the task of upper bounding the regret boils down to upper bounding the distributional G variation. And then we developed an algorithm to compute and learn a distributional G optimal design. For our batch elimination framework first, we will set the grids of batches in this manner, sort of like in a double exponential way. Here, the batch k is from tk minus 1 to tk, and we design it like this way so that when k is log t, this term is almost capital T. And for the elimination framework, for each batch, we first compute the confidence interval for each arm, this term, using the information obtained in previous batches. And for elimination, the idea is that if the confidence interval of arm I is less than, like if this is less than or equal to, is completely below the confidence interval of the other arm J here, which means that arm I is not very likely to be the best arm, so we would eliminate arm I. For example, here, notice that the confidence interval of arm 3 is completely below arm 5, so that's when we want to eliminate arm 3. Notice that here, elimination is not a new technique in Bandit algorithm, but usually we use uniform length of confidence interval in the same round of elimination, so that the regret analysis is easier. But here we have different confidence interval for different arms. At line 8, we have the set of survived arms AT, and at line 9, we will cleverly design a sample algorithm package to choose a survived arm from AT. And this exploration step is basically the most important step in our algorithm. Thanks to the elimination framework, we only need to focus on exploration in this step and do not need to worry about exploitation. In fact, the main technical difficulty in this whole algorithm is to find this exploration sample policy to learn as much information as we can of all the arms. By some technical analysis, thanks to the elimination phase, the regret incurred by arbitrary survived arms is bounded by this. Which, as you can see, that we already have a square root t type regret. So the main task of upper bounding the regret boils down to find an exploration policy pi to upper bound this. And we define this term as the distributional G variation because this is a stochastic form of the so-called G variation in optimal design. And I will explain this name in the next slide. Also notice that we assume the information matrix here is invertible. I will also explain the name information matrix in the next slide. If not invertible here, there is always some technical tricks to fix this problem. Notice that we call this term information matrix, and basically we want our sample algorithm pi to make this term larger, which means that we want to collect as much information of all the arms as we can in the exploration step. For example, if we use uniform sample policy, by some simple calculation, we can see that VD is defined as a distributional G variation. VD is at the order of decay, and the regret by this inequality is bounded by almost at the order of the square root of dkt. And if we use a sample policy called pi-g, which is derived from G-optimal design, and I will explain in detail later, the VD is at the order of d squared, and thus the regret upper bound is at the order of d square root t. Recall that the optimal minimax regret is almost at the order of dt. If here d is larger, then everything is solved. Is smaller, and then everything is solved here. We can already use this pi-g, and the regret is already bounded by they already matches. However, if d is pretty large, then log k is smaller, and this term becomes square root of dt log k. And then our problem boils down to, can we find a sample policy pi such that VD pi is almost at the order of d? Here is where we are going to use the so-called distributional G-optimal design as mentioned in the title of this paper, which is basically a stochastic extension of the G-optimal design. Okay, let's recall what is G-optimal design, which is a well-studied branch in statistical learning. So first, what is optimal design? Optimal design wants to minimize the estimation variances of parameters via designing queries to the given set of data points. And what is G-optimal design? It is optimal design using G-optimal criteria, which is to minimize the maximum estimation variance among the given data points. Mathematically speaking, it is like given data point set X, we want to find a distribution K supported on X to minimize the maximum estimation variance. And this term is the calculated variance. And the middle term, this term, we call it information matrix. However, in our framework, X is also stochastic instead of fixed. So we call our modification of G-optimal design as distributional G-optimal design. For example, here, we slightly change the form of the variance, and that's why we call it distributional G variation. You can see that when D is a singleton, this term is exactly the same as the variance here. So now what is pi-g? Pi-g is derived from a famous corollary of general equivalence theorem in optimal design, which basically says that for any x, there exists a distribution kx supported on x, such that the maximum of the variance can be bounded by OD. And such distribution can be efficiently found. You can see that if D is a singleton, the variance is already bounded by OD and everything is solved. However, in the stochastic setting, it is much more complicated. But inspired from this corollary, we can first try pi-g, which is defined as the distribution kx here. Here, x corresponds to the context vectors of the survived arms. Notice that, as I mentioned before, the distribution variance is in fact bounded by d squared. The calculation is simple and presented here. Basically, this step is just a simple linear algebra, and this step used the inequality of the corollary here. And let's go back to our most important problem in our algorithm. Can we design pi such that VD pi is less than or equal to the order of D? We affirm that the answer is yes. And furthermore, we can compute a parameterized form of such sample policy pi with a limited number of parameters. Here we use the mixed argmax policy. With half the probability, we keep the pi g part. And for the other half of the probability, we explore more on some certain good directions VI, and with probability PI, and choose the best term X for this direction VI. And we prove that for any distribution D, recall that D is a distribution of context vectors xti for all time t and all I. We can compute a mixed argmax policy pi with parameters pi vi, such that first, the number of parameters n is pretty small for d log d, and which means that the number of good directions we need to explore is for d log d. So the number of total entries we need to compute is limited, like around d cube log d. And then most importantly, the distributional G variation of such policy can be bounded by the order of d log d. The proof of this theorem uses the elliptical potential lemma, which is quite common and important tool in the regret analysis of linear bandits without batch constraint. But interestingly, the way we use the elliptical potential lemma is completely different. If you are interested, you can check our original paper for the proof. So here, when we know the distribution D, everything is already solved. But we don't know D in advance, so we need some extra work to learn this pi. A remark here is to have a more robust performance in the learning process, we can use a mixed softmax policy to compute a distributional G optimal design, since it is more stable and smooth. Okay, so what to do when we don't know D in advance? A natural approach is to draw some independent samples x1, x2, x gamma from D and hope that the policy pi learned from the uniform of these samples could generalize well to the true distribution D. However, this is not working since even when gamma is as large as the order of arbitrary polynomial of D, counterexample still exists. The high-level idea for the counterexample is, for example, here, there are many context vectors in a D-dimensional space we need to explore, and every time we can only get some samples like these blue dots. In some directions, the true probability may be large, like this direction or this direction. In some directions, the true probability may be extremely small, like this direction. In an infrequent direction, the empirical probability mass may be unbounded times larger than its true probability mass. For example, here, the true probability in this direction may be extremely small. However, if we have a sample from this direction, the empirical probability would be at least 1 over the number of samples. So how to learn pi in a sample efficient way? We cleverly designed a learning algorithm called core learning to solve this problem. The idea of core learning is to first prune the infrequent context directions, and then find a core which only contains frequent directions and use empirical distribution to approximate true distribution only on this core, and compute a mixed softmax policy on this core. For the infrequent directions, we argue that this part can be properly handled by the PyG component in a mixed softmax policy. Okay, so by now we have already proved our main theorem. We can use log t batches to achieve square root dt type regret. And we use the batch learning framework to have a square root t type regret and focus only on the exploration part. The problem then boils down to find the exploration policy pi whose distributional G variation is bounded by order of D. And then we compute and learn such distributional G optimal design using a technique called core learning. Besides prove that we can use log t batches to achieve square root dt regret on the stochastic context in batch learning model here, we also studied the amount of adaptivity needed to achieve optimal regret in linear bandits on the other models and settings, as shown in this table. In real policy switch model on the adversarial context setting, we also narrow down the upper bound and the lower bound up to some like polylog factors. Here, adversarial context means that every time the context vectors are drawn from different distribution dt, and these dt are chosen by an adversary, so it's harder to learn, and the learner has to minimize the regret in the worst case. Recall that in stochastic context, d is the same for all the time. And the real policy switch model means that the learner can freely switch the policy at any time, which means the learner would have more freedom than batch learning model. And the amount of adaptivity needed is measured by the number of policy switches. Okay, that's basically all the contributions of our paper, and thank you all for listening.